Hi there and welcome back. Let us look at this refrigeration cycle here using carbon dioxide to cool off water. I'll be using Aspen Isis. Prior to this, I've done actually a fun activity or fun example using CoCo Simulation. So I figured out why not also show you with a different simulation as well. So the first step here will be to use or to log onto your Aspen Simulation. Once you've logged in, you'll then proceed to go under component specification and add all your components. In this scenario, you only need carbon monoxide and water. Once you've added both these components, the next step will be to go to methods. Under methods, we are going to specify the base method as Pang Robinson. After this step, now on Aspen Simulation, we are just going to be clicking next, next, next until all our required properties have been calculated. My results are now available and all the tables that were required by Aspen have been generated. The next step now is to proceed and go to simulation. Under simulation, this is where now we're going to try and draft our refrigeration cycle flow diagram. Okay, let's start. At my equipment, I'll be starting with my compressor. Let's include a valve. We are going to add a heat exchanger that's going to act as a condenser. The heat exchanger whereby heat will be transferred between carbon dioxide and water. Let's try and connect the streams. Okay, it looks like I have to rotate my compressor. So I'll be rotating it on my vertical axis. I'll be connecting my streams from the compressor to our condenser, from the condenser to our expansion valve, from the expansion valve to our heat exchanger, from the heat exchanger back to the compressor. Also, let's connect the water inlet stream and the water outlet stream. Next step is just to label everything. So the first point will be the stream that's exiting the valve. So this will be stream number 1, carbon dioxide. Stream 2 will be the one that exits the heat exchanger. Stream 3 will be the stream from the compressor to the condenser. And stream 4 will be the stream from the heat exchanger to the valve. Also label our equipment accordingly. So we're going to have a heat exchanger, compressor, condenser, and expansion valve. The next step now is to specify some few components. Let's start with our compressor. For our compressor, we are going to say we want it to be isentropic, and our discharge pressure will be 60 bar. So we expect stream 3 to be 60 bar. For the heat exchanger, we are going to specify our outlet temperature to be 22 degrees Celsius at 60 bar still. For our valve, let us specify the outlet pressure. And we are going to say we expect the pressure of 60 bar. And we are going to say we expect the pressure of roughly at least 27 bar. Now, let us specify the inlet streams. We only have to specify 2. So I'll specify the inlet stream of the refrigeration cycle whereby carbon dioxide will be running, and that's stream number 1. In terms of mass, I will say I'm expecting 1 more percent or 100% of carbon dioxide and 0 water. Specify the flow rate within the stream and the conditions. We can say we expect the stream to be minus 9 degrees Celsius and 27 bar. Stream 6 as well. In fact, let's label it to H2O entering, where we need to cool. So we're expecting to feed in a warm water flow rate and expecting it to come off as a cool water flow rate. Okay, so for our inlet water stream, we can specify that we will be feeding 12 degrees Celsius at 1 bar, also in a form of mass. We can specify the mass flow rate to be roughly just higher than that of carbon monoxide. Okay, we've specified most of the parameters. The only thing that's short in here is the heat exchanger. For our heat exchanger, this carbon dioxide is entering at minus 9 degrees Celsius and water is entering at 12. That means the carbon monoxide stream is the cold stream. Still says we are not done yet, and that's because we need to specify the specifications. If you're not sure, always click next and it will guide you on what is shorting. So I'll specify that the temperature here is -1 degree Celsius. Now that we've computed everything, oh, it cannot determine which stream is inlet is hot, and okay, let's fix that. So I'm just gonna reconnect destination. It's still saying no. Perfect. Now the inlet streams are perfectly aligned. So I'm just gonna click next so it can guide us. What are we shorting with? Okay, so water. So it says we didn't specify the water stream. We did specify the temperatures, but not the components. So we only have 100% water and 0 carbon dioxide in the stream. Once satisfied and happy, now we can run our file. It says that while checking input specification, there was an inconsistency of water settings detected for 2 streams. Something to look into, definitely. Okay, so now I can actually go to my simulation and just look at our streams. Let us go to modify and just select some few parameters there, temperature, pressure, and the mass flow rate. It's solved nicely. I just need to look into this warning here. Stream 1 goes into our heat exchanger at -9 degrees Celsius, exchanges heat with the inlet water stream, and exits at -1 degree Celsius. The carbon monoxide stream that was used to exchange heat then gains energy or heat rather and goes to 22 degrees Celsius. The pressure here remains constant from the expansion valve all the way to stream number 2 after the heat exchanger. So our compressor here will be used to increase the pressure from 27 bar to 60 bar. Once it travels here, the temperature has increased due to the compression that occurred and the condensate, rather, that's why we have it here, to help us reduce the temperature. By using a cooling effect, the temperature will reduce from 100 degrees Celsius to 22 degrees Celsius. After it goes through an expansion valve, both the pressure and temperature will change. The temperature will drop to -9 and the pressure will go to 27 bars while it also dropped. The cycle then will definitely continue. So this process here is known as a refrigerant cycle, and it is used in most processes such as air conditioners, your refrigeration at home. It is a very, very complex process that's used in the industry. The reason why we have this refrigeration cycle here, this process here, was simply just to reduce the water from 12 degrees Celsius to -1 using a closed cycle. This carbon dioxide here will continuously continue to flow throughout the system from 0.3 to 0.4, 1, 2, just like that, as the water continuously the temperature cools off to -1 degree Celsius. So yes, guys, that's it. I really hope this makes sense. We also have the exact same example using a different software. This time around, we used CoCo Simulation. I'll also try this example for you guys as well using DW Sim to cater everyone's needs because we all prefer different simulators. Okay, now till next time. Bye.